All right, guys, so this is lesson 25.1. So this is a little shorter video, but it is complicated ideas, so we'll try to take my time and explain it in a way that makes sense. So in the last lesson, we just got done talking about magnetism, and we discussed how moving charges and moving current could create magnetic fields. So we talked about the the current in a wire creating a field, or that's how like magnetism is created in anything, is the electrons moving inside the mat. So in this lesson, we're going to look at the opposite idea and see about like, can a changing magnetic field create an electric current? Electric current that is produced by a changing magnetic field, and it is possible, is called induced current. So induced meaning like the changing field created the electricity. It's not because of a kind of voltage source. It's like this magnetism created the electricity, just like the electricity creates the magnetism. So we'll talk about those ideas. So in this picture, and I'm going to use a simulation to help kind of make this make more sense. We have a bar magnet. So this is our bar magnet here, and it's just being held at a fixed distance away from a coil of wire that's attached to an ammeter. So if you remember the FET simulation with circuits, the ammeter measures how much current is going there. So if you look, it's at 0 right now because it's just being still. So there isn't a changing field. Then in this next picture here, the magnet is brought closer to the coil of wire. So there's more magnetic field lines penetrating that coil of wire. And as a result, you get a current. So like the meter measured some current, and that's why the line is gone from 0 to some new number. Okay. Eventually, if we stop, it goes back to 0. And then it says when the magnet is moved away from the coil, another current is produced in the opposite direction. So if we take this magnet and we move it away from the coils of wire, we get another current, and it's in a different direction. So in order to have a current from this kind of demonstration or movement of charges, how to get the charges to move, you have to have an EMF, or you need a like potential difference, which we talked about in the electricity unit. So we said that current moves from higher, or charges move from higher, positive charges move from higher potentials to lower ones. So the changing the magnetic field that penetrates the coil of wire creates an EMF and produces a current, and this is called an induced EMF. So we have induced current or induced EMF, which are just currents or voltages that are produced by changing the magnetic field. So I'm going to go to this FET site. So this is slightly different than the one you guys are going to use, but it's a little more basic. So it's the same kind of principle. We have a bar magnet. You can see the field lines created by the bar magnet. We had talked about that in the last lesson. We have these coils hooked up to a light bulb, and it also has a voltmeter. So if this magnet is not moving, you can see that nothing is happening here. There's no induced current. There's no induced EMF. So the EMF is the voltage. If you had a current, that means the light bulb would light up. So if we take the magnet and move it towards the coil of wires, in our last slide that we were showing, there's an induced current. So the light bulb will light up, and the voltmeter you can see moving. I'll do that again. And the faster I do it, the bigger the induced current and the bigger induced EMF, because the light bulb has some fixed resistance. We can also change the polarity. So if I just click and flip the magnet back and forth and back and forth, you can see that there's a voltage and current produced. Okay, so that's just like the actual thing that this diagram is trying to show. It's just in an example. All right, so we're going to look at a different setup, but it's still the same idea. So in the figure below, we have we're going to examine how the induced EMF is produced and the current that happens because of this EMF. So we have a length of wire. So this vertical bar here is like a piece of wire, and it's moving at a velocity in a magnetic field. So the first question is, what is the direction of the magnetic field? So I'll let you figure that out looking on this diagram. So if we think about that, the magnetic field, we have X's going into the page, so the magnetic field is directed in. We are moving the wire to the right, so the velocity is to the right, and the magnetic field is into the page. So if we use our right-hand rule, the positive charges in this wire, or the current, would be pushed up to the top. So the positive end is at the top. So let me fix this because it's annoying me. Sorry. So this is the positive end up here where the positive charges collect. And if we have positives up here, then the negatives are at the opposite end. So that's kind of what happens. So if we had a positive charge here, and we have a velocity to the right and magnetic field going into the page, our right hand, the palm of our right hand would push up. So the force would act that way. So the magnetic force would push the charge upward, and the positive charges collect here and the negative charges collect here. Okay. As a result, we talked about that, and this separation of charges creates an EMF. So just like we had, like if we had a positive side and a negative side, we would have a voltage or a potential difference between these 2 points. Okay, so that voltage or EMF, that's the same thing. EMF, it looks like that. It's the epsilon. It's the same as delta V. I don't really care which one to use, but it's called electromotive force in this. So based on that, it says which way will the current move? So current is just the motion of positive charges. So our current is moving up. So our current is going upward. So the current in this wire, as it moves through, as we pull it to the right, it's going to create a current going up. That's the idea. All right. So we want to look at maybe just an individual charge. So if we examine just this individual one positive charge in that wire, if you imagine this is the wire that it's in, we said that the magnetic force is upward. So the magnetic force from the magnetic field is pushing up on it. If we had a positive end and a negative end, and we had a positive charge in the middle, which way would the electric force or try to act on it? So the positives would repel, the negatives would attract. So there's this electric force going down. So that's what this is here. And if the magnetic force and electric force are balanced, then the charge won't move. And this occurs when they're equal. So if they're equal, those two forces are balancing each other out. If we think about it as a free body diagram, they both have a charge in their equation. So QVB is the force on a charge moving through a magnetic field, and QE is the force on a charge in an electric field, which there's an electric field going from the positive to the negative. That's what's happening here. So QVB equals QE. The Q's drop out, and we get this idea that the velocity times the field is equal to, or the magnetic field is equal to the electric field. In the past, we've defined potential difference as E times D, where E is the electric field strength and D is the distance traveled in the field. So it's traveling maybe from the bottom of the wire to the top of the wire. So that's why we can replace it with L. And we can say that the EMF, or the change in potential there, is VBL. So we're just basically putting D on both of these sides, and that becomes potential here. So we got a new equation. So this is an equation that's useful if we know the velocity, the magnetic field, and the length of the wire that's moving through the field. All right. So kind of coming back to this idea, this current that is induced, so this is the induced current from the motion of this wire through this magnetic field, is actually creating a magnetic field itself. So if we think about a wire and the current's going up, we used a different right-hand rule to figure out the direction of the magnetic field that's induced. So this is the second right-hand rule, where you just grab the wire. So if you have a pencil or a pen, then you can imagine that's the wire. You just grab it with your thumb pointing in the direction of the current. So the current's going up, your thumb should point up. So kind of on this side, on the right of the wire here, we have the field lines going in. So I have X's for this part. And then on the other side of the wire, our fingers curl. On the left side of the wire, our fingers will curl out. Like when you grab that pencil or wire, it will come back towards you. So that's why we see dots here. So this is this what I'm drawing is the induced magnetic field. So this induced magnetic field is directed there. Also, when there's a current in a field, there's a force on it too. So like we can think about if this current's going up and the field is going in, if I use the first right-hand rule, there's a magnetic force from that current that is going to the left. So FB is going to the left. And if you think about it, we're moving it to the right and FB is going left. So what's it going to do? It's going to slow it down. That makes sense, right? Because in order to keep making this current or produce this current from this changing magnetic field, we have to apply a force to the right. If we could just get it moving and then it would just keep moving itself, if the force kept propelling it forward, we'd be creating energy out of doing nothing. And that doesn't make sense. So according to the law of conservation of energy, in order to get this current, we would have to do something. So we would have to apply a force to the right. So if we applied a force, which I'll call FA for applied, so if you imagine grabbing this bar and moving it to the right, then we can keep producing this current. If the bar stops moving, there is no more current. So if we got it moving and slid it, it would eventually slow down and stop because of this magnetic force that would act on it to try to stop it. Again, this is kind of confusing stuff. I understand that, but hopefully you're getting these basic ideas down, and we'll go over them in class too. All right, so let's take a look at this example. So it says we have a conducting rod, so a piece of wire or something going across here, and it's got a length of L, and it's free to slide between these two tracks. If a magnetic field is directed out of the page, so this arrow going this way, that's the magnetic field. They labeled B. It's a little hard to see in this diagram. And it says, in which direction will a current be produced? So if you imagine there's charges in this wire, the magnetic field is going that way. The weight of the actual bar is trying to pull it down. So the force of gravity is trying to pull it down. So if we think about it that way, you'd have to put your thumb in the direction of the force of gravity, which is the way the bar is going to move. B is the magnetic field, so the current is going to get pushed. The current's going to go that way, or the charges are going to get pushed that way. So the magnetic force. So this velocity, or I had it as FG. That's really the velocity of the bar. It's moving down. Then this is the direction of the current. So the current goes across this idea. And then if we think about it, if we have that current and the magnetic field is going the same way, there's a magnetic force that's trying to slow it down. So the magnetic force acting on this bar is up, and the force of gravity is going down. And again, that makes sense because the induced force acting on the bar or the wire is going to always oppose the direction of the motion. All right. It says if the length of the rod, same example or same setup, if the length of the rod is reduced by a factor of 4, which of the following will maintain the same induced EMF? So again, it's VBL or VLB. Let me just go back and show you that equation again. Yep. So E equals VBL. So we're trying to keep this the same. And it says if we've reduced this by a factor of 4, so we divide this by 4, in order to keep E the same, we have to get this to increase by a factor of 4. So without changing the speed, we can increase the magnetic field by a factor of 4. Yeah, I think that checks out. Without changing the magnetic field, we can increase the speed by a factor of 4. We can increase both V and B by a factor of 2. Yeah, they all three of those combinations are going to get us that constant EMF. All right. So that is, I think, probably the most confusing part. This next part is a little, I think, easier to visualize, but it's not, super simple. So we're going to talk about something called flux, and this is called magnetic flux. So magnetic flux is represented by the letter phi. It's a capital phi. And a magnetic flux is defined as the amount of magnetic field that goes through an area of a loop of wire. So if you imagine that you have some sort of loop or rectangle or some sort of area, it's like how much magnetic field is going through that area. So the way that you figure this out is this equation. So it's BA cosine theta. B is the magnetic field strength, which probably is given. A is the area at which it's going through. And then cosine of theta, theta is the angle between the magnetic field, the direction of the magnetic field, and the normal to the area. So in this diagram, these blue lines represent the magnetic field, and this black line going through, that is the normal to that ring or that area. So the angle between them would be theta, between that direction, which is perpendicular to the loop, or normal to the loop, and the magnetic field that's going through. All right. The unit for magnetic flux is something called a Weber, which is a Tesla meter squared, if you wanted to define that. So we're going to answer some questions about magnetic flux. And again, it's a little simpler in the beginning, but then it ties back into what we were talking about earlier. It's a little more confusing at the end. So in each of these diagrams, I have 3 diagrams here, A, B, and C, or well, actually 4, D. We're going to look at how much magnetic flux is in each of the diagrams. So you just really just have to count. So this one, there'd be 4 in this area. So we'll just say there's 4 lines. In this one, there is 6. If you count this area, 1, 2, 3, 4, 5, 6, 7 maybe. And this one is the one that sometimes people get wrong. There is no flux in this one. So this is 0 because the magnetic field lines and the area are parallel to each other. So like if you are the normal, they're at 90 degrees. So if you did cosine of 90, that is going to get you 0. So there is 0 flux when that happens. So when the field is not going in any sort of the same direction as the area, then you get no flux. So these lines are just basically like running across the top of the piece of paper, whereas these lines would go through the piece of paper. If you imagine it was like arrows penetrating and going through. If you look at these, this looks like it has a stronger field, but this has a bigger area. So this area, because it depends on both of them, if we had the same area rectangle in this, it would have a larger flux than A would have a larger flux than B. So it's really just like you're figuring out how much magnetic field goes through an area, and it's dependent upon the strength of the magnetic field, it's dependent upon the area, and it's also dependent upon this angle. So you could have, like I could draw our area to look like this. And because it's not exactly kind of, they're not pointing the same way, the normal to the surface of the area is not the same as the direction of the magnetic field. It is slightly less than it would be in C, but it's also bigger than D because it does have some lines that go through it. Okay, so the angle, it's again BA cosine theta. So all those things have an impact. All right, so induced EMF in a loop of wire is equal to the rate of change of flux going through it. So this is the equation for it. So rate of change, rate is just how much time it takes for it to change. So if you have a changing BA cosine theta, or changing flux, that divided by the change in time. The negative is represented in the direction of the current induced in the wire. The magnetic field produced by this induced current has to oppose the change in external magnetic field. Otherwise, the law of conservation of energy would be violated. So that's that idea that the induced, the direction of the current has to induce a field that opposes the changing field. So it always goes against it. So this example here will help us with this idea. So if you take a look at this example, there's a current going through this wire and it's going to the left. So if you imagine the current is traveling to the left and it's increasing. So it's increasing, the current is increasing, which is going to change the magnetic field. So last video we had B equals U naught I over 2 pi R. So that was the magnetic field strength created at a wire some distance away. So this wire is creating a magnetic field in this area or loop, in this kind of basically a wire in the resistor. So if I is increasing, the magnetic field is going to increase. So we have a changing magnetic field. Our area is staying the same because it's not changing. Our orientation is not changing. So cosine theta is not changing. These are constants. Cosine theta and A are constants, but there is a change in B, and that happens with time. So if we have a change in time and a change in flux, which is what's happening here, then we have an EMF. And if there's an EMF, we get an induced current. And remember, that current has to oppose the changing field. So let's figure out what kind of field is produced by this wire first. So the external field, essentially, is what we're talking about here, because the induced one is going to be the one that the current produces in this loop, or it's producing one in the loop. So this wire, if we think about the right-hand rule again, if we use right-hand rule number 2, we grab the wire and put our thumb going to the left, we would have kind of our fingers going into the page above it, and it would be dots below it. So I'm just putting dots down here. So like if you imagine when you grab that pencil or wire going to the left, your fingers would on the top would be going away from you, and underneath that pencil or wire, they'd be coming back towards you. So there's an increasing amount of lines going in that area. So we have, like, because the current's increasing, we get a bigger number of field lines going in. So what has to happen is the induced current has to send lines going the opposite way to try to cancel out that increase, because it always opposes the change. So if there's an increase going in, we need more lines coming out. So we have our fingers that are from the current that goes through that loop is going to come out of the page. So I need to grab the loop in a way to make it so that the field lines would be the red dots coming towards you. So to do that, I need a current that's going to go like that on the bottom wire, and it's going to follow along and go across the resistor like that. So it loops around in that kind of way. So if you imagine grabbing the bottom wire and you wanted to make your fingers curl towards you when they came back above that wire, in the resistor it would curl towards you when you went across this way. So this direction is what we're talking about. So it's going to be to the left. So that's a complicated way to get to the idea, but essentially what you're trying to do is you're trying to cancel out the change in flux, and the current that's induced is creating a magnetic field that is opposing the external magnetic field. So however the external magnetic field changes, the induced magnetic field is going to oppose that change, and the current has to produce that opposition. All right. Otherwise, the law of conservation of energy would be violated. Okay, so this video is a little shorter. It is a lot, and it's a little confusing, but it's the same ideas we talked about a couple different times. So again, this is the same idea I was talking about on the last slide here. So the current is going up because there's a bigger area here. There's a bigger flux. Going in, we're going to send lines to go the opposite way. So we need dots on this side. So the induced current has to go that way. It has to produce the magnetic field that opposes that. And the force that is applied has to counteract that drag force. Okay, so I'll stop there. We'll go over that in class for sure. So hopefully, whether you're watching this previous to class or after class, it'll make more sense then. All right, talk to you guys later.